Welcome guys to example 3 of solving ordinary differential equations through undetermined coefficients. So we are given this problem, y prime prime plus 2y prime plus y equal to 4 sin x. Okay, it is a hyperbolic situation where we have the right hand side to be a hyperbolic function. So let's dive in to see how the solution looks like. Solution. So there's something unique about these kinds of problems. Okay, we're given, first of all, y prime prime plus 2y prime plus y equal to 4 sin x. Okay, and we want to solve for the solution of this particular differential equation using undetermined coefficients. The first thing that you need to do anytime you're given a hyperbolic right hand side is to transform this particular right hand side to its exponential equivalent. So I need you to just recall, okay, when you have sin x, that's the hyperbolic sin x, it is exponential x minus exponential minus x over 2. Okay, when you have sin ax, where a is a constant, it will be exponential ax minus exponential minus ax over 2. So when you have cos x, for instance, it is exponential x plus exponential minus x over 2. Similarly, when you have cos ax, we're going to have exponential ax plus exponential minus ax over 2. So these are identities that will be handy when you're dealing with hyperbolic cases. So transforming the right hand side, we have what? Y prime prime plus 2y prime plus y is equal to 4. Then sin x becomes exponential x minus exponential minus x over 2. Then if you keep on going, you're going to get 2 going into 4 is a 2, so you have 2 exponential x minus exponential minus x, and this is 2 exponential x minus 2 exponential minus x. So the differential equation now reduces to y prime prime plus 2y prime, okay, plus y is equal to 2 exponential x minus 2 exponential minus x. Okay, so this is our differential equation. Now that we have transformed it to its exponential equivalent from the hyperbolic equivalent, we can now go ahead to obtain our complementary function and particular solution as follows. So recall, for this problem, y is equal to yc plus yp. So let's begin with yp. So for yp, okay, we have our yp. What is the form that yp is going to take? So looking at this right hand side now, I can see an exponential x and an exponential minus x. So there are two types of exponential function here, the positive exponential and the negative exponential. Okay, so one is growth curve and another one is decay curve. Exponential x is usually tied to growth curve and exponential minus x is tied to decay curve. So I'm going to assume a random generalization for the growth rate or the growth curve, which is a exponential x, and I'll assume a random generalization for the decay curve, which is what? B exponential minus x. So this will be the form of my particular solution for now. So let me call it equation 1. So I am going to find my yc, okay, and whatever I find in my yc will determine whether this particular solution remains the way it is or we are going to modify it. So let's find yc. So for yc, for our complementary solution, our complementary function. So you need to consider when the differential equation is equal to 0. So when you consider it like this, the characteristic equation is given to us as from this equation. Let me use a variable m, so I'll have m squared plus 2m plus 1 equal to 0. Okay, so if you solve for m using quadratic formula, m, or using factorization, you can get m plus 1 equal to 0. Okay, when you factorize this, then m is equal to minus 1 twice. So this is a case of a real and repeated roots. So for real and repeated roots, our complementary solution is going to be given by c1 exponential, okay, minus 1x, okay, and plus c2, then you now multiply it by x and exponential minus x. Okay, so this is the form of our complementary solution. Now that you've gotten your complementary function or your complementary solution yc, so you have to recall that yp is equal to a exponential x plus b exponential minus x. Now before this yp can be valid, okay, before it can be valid, we need to make sure that there is no term occurring in this yp, okay, that occurs in the yc that we've gotten above. But if you look at it very well, you discover that first of all, starting with this term exponential x, if you look at your yc, there is no term in exponential x. Okay, so this particular term is safe, this particular term is valid. Now going to this next term, you have what? An exponential minus x, a term in exponential minus x, and sadly we also have a term in exponential minus x in the complementary function. So this is a special case. This repeatedness is what we call resonance. Okay, resonance. Okay, so it's called resonance when you see repeated terms. Okay, let's ignore the coefficients this time around. So when you see repeated terms in a particular function occurring in your yp and in your complementary function, it's called resonance, and as much as possible you want to offset that resonance. So because of the repetition of exponential minus x, okay, in the complementary function as also appearing in the particular solution, we're going to modify our yp, okay, by offsetting the repetition or offsetting resonance by multiplying this term by x. So we have a exponential x plus b x exponential minus x. So this is now the modified yp. But wait a moment, now that we have modified our yp, we can now see that there is also a repetition now. Okay, this particular term occurring in yp has now repeated here in yc, and we don't want this, so there is another resonance happening. So we also need to offset it by also multiplying this term by x again. So your yp is equal to a exponential x plus what? B x squared exponential minus x. So having offset yp in this particular way, you can now see that there is no repetitions. Okay, our yp is free of any term that repeats itself in yc. Okay, so you have to make sure that your yp does not have any term that repeats in yc. Okay, if there is any term like that, you need to offset by multiplying that term in yp with x or with your independent variable. So this is the yp that we are going to be working with. Okay, and of course yp should satisfy this is your particular integral, it should satisfy the differential equation given to you. So yp should satisfy the original differential equation that was given to us, which is y prime prime plus 2y prime plus y equal to what? 4 sin x. So it should satisfy yp prime prime plus 2yp prime, okay, plus yp is equal to 4 sin x, and 4 sin x was later corrected to 2 exponential x minus 2 exponential minus x. So 2 exponential x minus 2 exponential minus x. Okay, so we want that yp should satisfy this particular equation, okay, here. So that means we need to obtain these terms yp prime and yp prime prime. So yp is now given to us as a exponential x plus bx squared exponential minus x. So this is 5. Then we have to obtain our yp prime. So when we obtain our yp prime, before we obtain yp prime, let me teach you something very important. Okay, you find this very handy when you're solving ordinary differential equations. Now, when you want to differentiate with respect to x, when you're differentiating a product u dot v once, of course you use product rule, okay, and this will give me u prime then v plus u then v prime. Is that okay? You differentiate one, you hold the other, then you hold the other, you differentiate the other. Now let's make further product rule. Okay, I want to teach you something extra. I must have taught this in another video in the past, but just in case this is the first video that you're watching of this channel, let me teach you further product rule. Further product rule is when you're differentiating, let me say, more than one times a particular product u and v, okay, the x squared. So in other words, I want to differentiate this product two times. So to differentiate this product two times, it should just follow some kind of Pascal's triangle combinatorial coefficient or binomial expansion rule. It's just that first of all, we are going to have u prime prime, we'll differentiate u two times and we'll keep v. Is that okay? Then we'll now put our combinatorial coefficient, which is 2 in this case. We're now going to differentiate u once, differentiate v once, and finally we are going to hold u and differentiate v two times. Is that okay? So this is further product rule when you are differentiating a function two times. So you'll be asking, where am I going to apply this? So let's see how we are going to apply it in obtaining our yp prime and yp prime prime. Okay, and yp prime prime prime. So yp prime, sorry, in obtaining, let's see how we are going to apply this in obtaining yp prime and yp prime prime. So let's begin the differentiation. If you differentiate this, you're going to get a exponential x. Then when you differentiate this, I'll suggest you take this whole as u, okay, then take this as your v. So when you differentiate, you have to what? Apply product rule. First of all, you differentiate this, it's going to give you what? 2b x, then you keep exponential minus x, and finally you're now going to hold your bx square, and when you differentiate exponential minus x, you're going to get minus exponential minus x. Is that okay? So this becomes the expression for yp prime. That is question 6. So let's find yp prime prime. Let's find yp prime prime. So to find yp prime prime, you are going to differentiate this guy just once. So if you differentiate it, you're going to get a exponential x. So the tendency will now be to come from here and start differentiating this one once again, right? So if you do that, you're still going to get some kind of equations that you have to simplify, and okay, in this time around I'll have to apply product rule two times again. That's apply product rule here and product rule here. But another way to bypass this is to go back to the original one and differentiate this guy two times. Okay, so we'll differentiate this guy 2 times rather than differentiate this with product rule and differentiate this with product rule. So you can actually differentiate this with product rule and differentiate this with product rule and match the answers, and you get what you want. But we don't have the luxury of that time, so we can easily differentiate this one 2 times directly from equation 5. Okay, so that we'll get the other expression remaining here. So I'm going to follow this convention I've introduced here. Okay, that will make things simpler for us. So I now have plus. So the first thing is, since this whole term is my u, bx squared is my u, and exponential negative x is my v. So the formula says differentiate u 2 times. So we're going to differentiate what? Bx squared 2 times. The first time we differentiate it, we're going to get 2bx. And the second time we differentiate it, we're going to get 2b. So you have 2b. Is that okay? 2b. Then you keep exponential minus x the way it is according to the formula. We have satisfied this term. Then I'm now going to go to the next step. So in the next term, I have 2. Then it says I should differentiate what? U. So this is my u. Differentiate u once. When we differentiate bx squared once, we're going to get 2bx. Then it also says differentiate v once. When you differentiate exponential x minus x, rather, you get negative exponential minus x, like this. Okay, then finally in the last portion of the formula, we now have plus. U is going to remain as it is, which is bx squared. Then you're not going to differentiate what? V 2 times. Okay, so in differentiating v 2 times, we want to differentiate exponential minus x 2 times. The first time you differentiate it, it will be minus exponential minus x, and the second time you differentiate it, it will be minus exponential minus x, which is exponential minus x. Is that okay? So you can now simplify your yp prime prime to be a exponential x plus 2b exponential minus x, and plus, when you open these brackets, you're gonna sorry about that plus sign. When you open this or expand this, you're going to get minus 4bx exponential minus x, and you now have plus bx squared exponential minus x. Okay, so this is what we have for our yp prime prime. So we're now going to slot the values of yp prime prime, yp prime, and yp into this equation over here, and compare the values in order to determine the undetermined coefficients a and b. So starting with yp prime prime, we have a exponential x plus 2b exponential minus x minus 4bx exponential minus x, and plus bx squared exponential minus x. Okay, so this is my yp prime prime. Then yp prime prime plus 2yp prime. So 2yp prime is this expression over here for yp prime, which is a exponential x plus 2bx exponential minus x, and minus bx squared exponential minus x. Okay, that is the expression for yp prime. Then finally plus yp prime. So for yp prime, I have a exponential x plus bx squared exponential minus x. Okay, and this should be equal to let me just write it here. We have 2 exponential x minus 2 exponential minus x. Okay, 2 exponential x minus 2 exponential minus x. So now that we have it in this way, what we want to do is we want to compare, okay, or we want to collect the like terms first of all. So collecting the like terms may be a little bit long and stressful, but let me show you how to do it by observation. So first of all, let's collect all the terms in exponential x. Okay, collect all the terms in exponential x together. Collecting all the terms in exponential x, I'm going to have a, starting with this guy here, the coefficients. So a plus, so for this term, if you open this bracket, you get 2a. Okay, and finally for this one, you have a plus a. Then this is exponential x. So the next thing you want to collect is all the terms in exponential minus x. So let's look for another occurrence of exponential minus x alone. So the only occurrence of exponential minus x is a 2b, okay, on exponential minus x. So the next occurrence is x exponential minus x. So we are going to find all the occurrences of x exponential minus x. So it occurs here, okay, it also occurs here, and I think that's it, right? So let's be sure we didn't miss anything. So for x exponential minus x, okay, we now have plus. First of all, starting with this term, the coefficient is negative 4b, okay, then plus. So going over to this term, it's actually 2b in the bracket, but because of these two outside, we're going to have 4b, okay. So you have x exponential minus x, okay. Then finally you go to x squared exponential minus x, okay. So starting with this term, the coefficient is b, is that okay? Then going over to the term inside the bracket, we have the coefficient as minus b, but because of these two it becomes minus 2b. And finally, when we check here, okay, we'll have plus b, and this is x squared e to the what? Minus x, and this is equal to what? Very good, 2ex minus 2e minus x. So if you simplify these brackets carefully, b plus b is 2b, 2b minus 2b is 0. So this one reduces to 0, this one also reduces to 0, okay. So what we are now left with, is when you simplify this, you're going to get 4a exponential x plus, when you simplify this, you get 2b exponential minus x is equal to 2 exponential x minus 2 exponential minus x. So permit me to copy this solution, because we're going to go to another section of our page now. Okay, so this is what we got previously, okay. So how do we now compare the coefficients? So for terms in exponential x, on the left hand side, the coefficient of exponential x is 4a. On the right hand side, the coefficient of exponential x is 2. So for 4a equal to 2, a is equal to 2 over 4, and this is 1 over 2. So for terms in exponential minus x, on the left hand side, the coefficient is 2b, and on the right hand side the coefficient is negative 2. So b is equal to negative 2 over 2, which is equal to minus 1. Is that okay? So a is 1 over 2, b is minus 1, and voila, we've gotten our undetermined coefficient. So where do they apply? They apply in what? Our yp. So our yp, the expression we had for yp was a exponential x then plus bx squared exponential minus x. So with the constants a and b gotten, the constants a and b are our undetermined coefficients, which by now we have determined them. So we have 1 over 2 exponential x, and I have minus x squared exponential minus x. Is that okay? So when you solve this equation, finally for your general solution, yc plus yp, then our y will be equal to, what is yc? Our yc was gotten as, if you could remember, we got our yc as this, c1 exponential negative x plus c2x exponential negative x. So back to this place, so we have our yc, c1 exponential negative x plus c2, we have x exponential negative x, and plus yp. So we have plus, let me see, exponential x over 2 and minus x squared exponential what? Minus x. So another way of arranging it is, you can say y is equal to c1 exponential minus x and plus c2x exponential minus x and minus x square exponential minus x. So I'm just trying to like follow the polynomial in terms of x. We have x raised to the power 0, x raised to the power 1, x raised to the power 2, and I'll now put my exponential x over 2 over here. So this is where you stop for this particular problem. This is the general solution. Okay, this one was quite long, but if you followed me up to this point, I hope you have learned a lot. When you are solving it on your own, you should be able to be more faster than I am now. Me, I am the one explaining it to you, so definitely when you're solving it on your own, you should be faster than I am, because I am doing explanation while solving, but you back then in your own corner, you'll be solving on your own without having to explain to anyone, unless of course you want to teach someone else, which will be very very helpful, 100% beneficial to you. So I hope you learned a lot of things in this particular video, and efficient ways to solve a problem. I will see you again in another problem on undetermined coefficients. But for now, take good care of yourself, and see you next time. Please like, share, subscribe, hit the notification button to stay updated on the videos for this channel. Thank you in anticipation for your cooperation. Alright, bye again.